I haven't been that have much of experience in West Africa, but in the dry beds and wetlands, I know quite a few. So that this session, we will have 6 presentations to giving you the ideas of that recent research, technology advancement in the field, in the application. So maybe we should start with the first presentation, but unfortunately the first one is not yet ready for the presentation. Maybe I would like to invite Kenya from Cameroon to start the first presentation, and then we will follow up with the other consequent time for that. So Kenya, please start with your presentation if you are ready.
Combining dry beds and vertical flow constructed wetland for Faecal sludge dewatering and leachate pollution. As you know all, developing countries rely from 90 to about 100% on on-site sanitation for excreta disposal. What does this mean? In Douala and Yaoundé, the two main cities of Cameroon, it is about 2,200 and 2,086 cubic meters of raw fecal sludge that are collected every week and that need to be disposed properly. Unfortunately, the few sewage systems that existed is damaged, and the treatment plants that existed to treat that is the activated sludge is no more functioning. They are all abandoned. So fecal sludge are collected and disposed without treatment. Therefore, we assist the direct dumping of fecal sludge with an accumulation in lowlands of this waste, causing land and environment degradation, and of course, leading to health risk when it comes to use wastewater in agriculture and other uses. In West Africa, there are attempts to tackle this problem, notably in Ghana, where the inhabitant sand filters have been tested for fecal sludge dewatering. In Cameroon, we have been testing since 2004 dry beds, especially dry bed planted with Cyperus papyrus and Echinochlora pyramidalis. So we come out with Echinochlora pyramidalis as one of the best plants that will be used for the purpose. And I think Senegal is now taking that at a full scale for the treatment of the sludge. These technologies have shown to be good in spirit, solid, and liquid phase of the sludge, and at the same time are shown to be good in plants production, and it has shown to remove more than 80% of the contaminant contained in the raw fecal sludge. Unfortunately, the leachate that is produced is still not good enough to be discharged or reused. That's why we, in this present work, are testing vertical flow constructed wetlands for the polishing of the leachate obtained from the dry beds. So to do that, we set up a treatment unit plants at the pilot scale made up of, we have 2 sets of beds. The first set, which is made up of dry beds planted with Echinochlora pyramidalis, and which beds are fed by raw fecal sludge in a charge of 200 kilograms per meter square per year that have been previously tested as one of the best load for the good functioning of dry beds. And from these drying beds, the liquid fraction, which is called the leachate, is collected and applied on the second set of beds. Here have the vertical flow constructed wetlands for the polishing of the quality. And for this polishing, we have been testing 3 hydraulic loads, 50, 100, and 150 millimeter per day, to see how the hydraulic pool affects the performances. And also we look at the feeding frequencies, since this has been shown to also impact on the performance of vertical flow construction. So for the performance, we just monitored physical, chemical, and bacteriological parameters in the raw fecal sludge, in the leachate, and in the effluent, that is, in the leachate before treatment and the effluent after treatment. Dear participant, we observe that organic matters were effectively removed from the system, where we had about 90%, 92% removal from CO2, chemical oxygen demand and biochemical oxygen demand. And whatever the hydraulic loads that were tested, we found that there was no significant difference in applying 50, 100, and 150 millimeter per day. The quality of the effluent complied with the requirement of the Cameroonian standards for wastewater discharge. We also found that the system effectively removed nitrogen, but the removal was not that efficient since the concentration for total nitrogen still exceeds both the Cameroonian and the WHO guidelines. But for phosphorus, it was obvious that the system removed these contaminants and the effluent concentration met the standards, the requirements for discharge. Still, without any significant difference between the hydraulic loads, nor do we observe any significant difference coming to the feeding frequencies in applying 1, 2, or 3 times the higher loads of 150 millimeter per day. Concerning microbial contamination, the system was not that efficient in removing fecal coliforms, nor did the hydraulic loads have an effect on that removal. But we found that when we applied the higher hydraulic load of 150 millimeter per day into 3 distinct applications separated by 5 hours of resting periods. The effluent concentration comes down less than 2,000 uniform quantities per 100 milliliter, which complies with the Cameroonian standards of wastewater for discharge, although still above the WHO guidelines, which is 1,000 for equal. We look at the plan of response to the operation and found that when we increase the hydraulic load, there is an increase of plant density. This implies that in a case the plant used here is a plant of economic importance, increasing hydraulic loads is good for that production, for plant production. So, dear listeners, what we can see it is that when we combine drying beds to vertical flow constructed wetlands, we have a comprehensive treatment of fecal sludge. And working application here should be that we apply for Cameroon, since the fecal sludge characteristics in Cameroon are a bit different from what is obtained elsewhere. So applying raw fecal sludge at 200 kilograms per meter square per year, followed by an application of the obtained liquid at 150 millimeter per day, applied in 3 times with a 5-hour resting period, enable us to have good quality except for nitrogen. These treatments can generate end products for use like biosolids, high nitrogen effluent quality, as well as plants for foraging. Of course, we said this treatment does not meet the nitrogen requirement, nor the WHO requirement for fecal coliforms. High hydraulic loads are preferable when it comes to produce forage. It is a treatment that is cost effective compared to the classic vertical flow construction made of many beds in series. So we can end this presentation without thanking all the organizations and funders who render this success possible, and also without thanking the Bill and Melinda Gates Foundation and also the FSM Organizer Committee for making us coming here today. Thanks for your attention.
Okay, thank you very much, Kenya. So we have time for a couple of questions. Yes, please.
I am Deepak from English Bangladesh. So it's a good presentation. In your presentation, you mentioned that high hydraulic load good for plant production. So can you mention what type of plants you consider? And the next question, you mentioned that this treatment plant is cost effective. So did you do any cost-based analysis regarding this? Thank you.
Okay, thank you for the questions. When we use 50 100 and 150 millimeters per day as hydraulic loads, we found there was no difference, significant difference. That means that vertical flow constructed wetlands could function at this high hydraulic. I call it high compared to the 30 to 60 millimeters per day that is commonly used in Europe as the optimal hydraulic loads. And at that hydraulic load, we have a good plant production, meaning that since here we use Echinochlora pyramidalis, which is a forage plant, it means has byproducts. Using that hydraulic load enables producing more forage, which can sustain the treatment. Now, regarding the cost effectivity, it's true that I've not done the cost analysis of it, but I just went on the basis that a classical vertical flow constructed wetland is made up of many series of beds. But here we are using a single bed. So I'm sure that there is a cost reduction of the system.
Okay, maybe the question let's ask one.
I'm Tiffany from FSM3 Laos. So I have two questions. The first question is concerned to the laboratory results. Because in my country, on-site sanitation is quite a lot. It's almost 95% is on-site sanitary. But most of people use chemical to clean the toilets. But how we can remove the chemicals when we use the drying beds? So because I'm not that seen for that. And the second question is because I'm not sure with the plants that we had applied the fertilizer. So if we apply the sludge as a fertilizer to the crops or vegetables, can we ensure that it's safe enough to eat directly? Thank you.
Okay, thank you for the questions. Regarding the analysis, we can say that in fecal sludge, especially what we have in Cameroon is that the fecal sludge is mainly from pit toilets. And pit toilets, they are structures that can last about 10 years without being empty. So the fecal sludge, the sludge is really stable. And therefore, we found that there was less heavy metals in these fecal sludge. And regarding the impact of the reuse of especially the biosolids in agriculture, there is a study one of my colleagues will have to present on the co-composting, and that has shown that the heavy metals are removed during the composting of the biosolids. So we can say at that level that the risk is minor.
The last question.
Thank you for the presentation. Like I mentioned from New Zealand, the heavy metals, if you reduce 8% of the heavy metal in your drying beds, I assume they are transformed to biomass growing on top. Is the product you are growing is it safe to apply to agriculture or cement?
I think the next presenter will answer that whether, because he worked on composting the biosolid which keeps most of these heavy metals. So he has a presentation on how these heavy metals are maintained through bioaccumulators acting in the composting. So we will have more clarification when he makes his presentation.
May I ask you a question? What is the temperature, average temperature and pH of that
Of the water. The temperature
is about 25, which is the actual temperature in Hanoi. And the pH is ranging between 5.5 to about 7.2. This is the temperature, the range of temperature that we have in the different regions and the frame that we obtain. And I will say that our water is a bit acidic. The pH of waters in Cameroon are around 5 to 6.
Okay, thank you very much, Kenya. I think that we have to have big hand for you. He is from Switzerland, I hope, as he mentioned, but actually he is from West Africa and Senegal. And we will talk about the impact of the sludge characteristics on planted dry bed, which may help respond to the questions we have for presentations. So please start.
Hi everybody, I just want to mention that I am working in part with Yawak and the University of Dhaka. So I am doing my PhD at the University of Dhaka. I can say for the introduction that nowadays planting dry beds are gaining more and more interest in the context of because by this technology we can have water for animals, biosolid for agriculture, and water for irrigation. But in the context of optimizing this technology, we need specific guideline for each climate zone. And we know in sub-Saharan Africa we have almost 3 climate zones. For that, we need to build some guideline for each climate zone, as in Senegal we did this experience to see how it can go. Then we can say that in European countries, planting gardens are renewable technologies, and high expertise are gaining in how to load how much load, in which frequency, effluent treated, and plant that can be used in the treatment of the sludge or the phosphorus. But sub-Saharan Africa lags behind in the design and the operation of the planting drying beds. And this technology is still at an experimental stage, with some results in sludge loading rate, in the loading frequency actually used in almost sub-Saharan African countries, the type of sludge treated almost FS, and the type of microphytes is equivalent. Some questions are remaining. Can this loading frequency be used in single-arid climate zone as we said? What is the behavior of the bed that all the type of effluents, like phosphorus, sludge, and sickness sludge that are actually produced in that? And echinoclora have been defined as the best plant, and we need to compare the function of this plant with other plants used long time in planting drying. That is the objective of our study, PhD study. In this PhD, we look for the burst frequency, the types of the type of incoming sludge, in the purification performance, and the biosolid stabilization. But for today, I will present the result of the type of purification. The methodology consists of 6 steps, and we have the experimental bed consists of 2,200 liter barrels with 90 centimeter and 50 centimeter diameter. This barrel with filtrating layer consists of 10 centimeter of coarse gravel, 10 centimeter of fine gravel, and 15 centimeter of sand. And at the bottom we have the drainage pipe. The second step is the plantation is the kilogram land, 934 square meter, and at this step water is developed. The third step is acclimatization phase, and we at the first stage we water is step water until the regrowth of the plant, and after this regrowth we water is starts for a month. Then we can see the development of plant. The load increasing is the next step, and here we increase gradually the load from 50 to 150 kilograms per square meter per year for 2 months. And the next step was the operation at the loading unit. Here we use 2,000 kilograms per square meter per year, and we load with FS directly dump, emptied from septic tank, FS signaled in the signal and septic tank, signal and septic tanks, and was sludge once per week. And the duration is 9 months. And the last phase is the maturation without loading for 3 months. Assessment of filtering capacity, the dryness of accumulation, and the chlorine. This is 3 parameters. And we monitor the performance of purification, and by this equation we calculate the removal rate. The biosolid are sampled in 5 points with a handover, and the sample are drying at the lab temperature and sieve at 2 millimeter sieve, and we look for physical chemical parameters as well as eggs and derivatives. For the result, we can say that comparing the concentration of the sludge used in this, we can looking for the TS that we have 10 times or more, 5 times concentration than FS, and this lead to 15 liter, 10 liter and 20 liter for the volume loaded with these 3 types of sludge. This lead to the low volume coefficient on collected with these 2 types of sludge, like FS from septic tanks and was for the sludge, a low clogging percentage and high drainage. That can be influenced the development of plant. We see in this slide. You can see that in the dry season plant have development problems, and we can see with the density here that the density is lower with this type of plant. But in the rainy season, plants start to regrow well, and we can see that the density is close. And this picture shows that we cannot find any difference between these plants. The pollutant removal, you can see that no difference for TS and COD, TSS removal, because the physical phenomenon are the main removal processes, and low mineral removal in bed FS from septic tank, V-shaped concentrated than the Senegalese standard, as you can see in yellow here. And we found some statistical difference in DSCOD and NO3 removal, as you can see here, with the ANOVA test. For the biosolid, we found that biosolid are almost, all the biosolid are almost stable with close value, and if we compare the matrix biosolid found in the literature, we found that it's and the last slide is the element X, and here we found 3 months of maturation are not sufficient to achieve spatial reduction. And we can see in this slide that the concentration of metals are well below the European guidelines. So I want to the conclusion to say that I for this research should contribute inferior to loading or transfer whoever frequency should then be used to improve plant growth and locality. Therefore, standard shape should be undergo pollution step beyond research for use in irrigation, planting driver active transport, any type of sludge, multi-purpose, geotrim of sludge should undergo annual maturation for irrigation as I. But following these 3 months testing could potentially be safe for use for other use than food products. Thank you for the attention. I wanted to acknowledge this resolution.
Thank you very much, Dr. Sampo. So, have a few questions, please. Yes, please.
Hi, I'm Asim from India. For both the presentations, what I saw that you both are talking about planted sludge drying beds. From the country where I come, space is an issue and it's high cost also. For planted drying beds, you have a cycle of around 9 months. Drying cycle of 9 months. But a sludge drying bed will have a 15-day cycle or 20-day cycle. So what will happen if we have a simple sludge drying bed rather than a planted sludge drying bed? What?
I don't understand.
Hello?
No plant.
No plants. Actually, this technology is in the Sanitation book also. The plant book that in that.
If you have no plant, you have just to work for what shorter cycles, like 1 month or 25 days, depending on the climate zone and the rate of dryness. The dryness can define the period of sludge of each campaign. If you are in zone that when you have a higher temperature, you can shorten your campaign. But if you were in Europe as your temperate climate zone, you can the campaign will be longer.
You have mentioned that planted drying bed is made from natural compost. So, did you do any comparison with the unplanted compost?
Not yet, but we have tested with some master students the unplanted compost and the co-compost with co-compost fecal sludge with, yeah, but we have not yet done this experiment. But I have the result of the unplanted drying compost, but I haven't made the experience at the same time with the same sludge. So I cannot compare very well because the fecal sludge change very well. It's not stable. It's very variable. So if you want to compare the same fecal sludge, unplanted or planted compost, you have to use the same sludge to have the representative compost.
I wanted to know how many plants you use per square meter. Then how do you remove that dry sludge? Then what dryness are you aiming at from that bed? Then last I talked about you recommend settling of the sludge following it onto a drying bed because it causes clogging. The questions, I was asking which percentage of dryness are you aiming at? How many plants are using per square meter? Then you talked about settling, that you should allow it to settle following it onto a drying bed. I was asking, because it causes clogging, that's what you said. I was asking, do you then load the spanatan or you load the settled sludge? Then the last question was,
I use 9 cutting per square meter. I show it in this slide. Yes, 9 plant per square meter, and we remove the sludge at the end of the maturation phase. And at this time, plants are almost dead, and we can remove easily the sludge, the accumulated sludge for the analysis. And the percentage of dryness is between, I show it here in the last slide. This slide, you can see the percentage of dryness at the end. And at the end of each campaign, we measure the percentage of dryness. Vary between 60 to 70 for this type of concentrated sludge as FS from settling tanks and wastewater sludge. And for the FS directly emptied from septic tank, we have a dryness between 50 and 60. So it's very in this one.
Thank you. Maybe short questions.
Shamsulullah from Bangladesh. Thanks for your presentation. If I want to use the compost in agriculture, especially for food production, so I am very much interested to know, have you studied on some worms like helminth, which is harmful for the food production?
Which
Helminth, some worms. If I want to use the compost in food production in agriculture side, so I have to study on the helminth or something like this worms. Have you studied on these worms?
No.
Okay, thank you very much. So, which also come from the Senegal that Saidu from the laboratory of wastewater and chemical sludge treatment and polarization from Senegal. So he will present about from waste to resource to fuels and forage like this.
Thank you very much, Mr. Sam. I want to present you my student on this topic from waste to research. So as far as we see Faecal sludge was a kind of challenge for communities with anticipation of settlements and urbanization. And as far as it was considered as waste, we faced troubles to how to handle it. This is how it was in 1780 in Paris. People were throwing the Faecal sludge from the window. Then, with some rules, they allow them to throw it on the river. Those rivers were also used to provide drinking water. And it's now in 2015 in Senegal, this is dumped in the groundwater. This ended with outbreaks on environmental pollution and fruits. But when communities began to look to Faecal sludge as resource, they began to handle it fairly properly and then use it like to feed fish as fertilizer. And it was amazing to see, since the 6th century before Jesus, Ezekiel was relating that at that time in some areas, Faecal sludge, that was used to burn or to cook bread. Now we are trying us to prove that Faecal sludge is or has calorific value that are comparable to, you are trying to convince ourselves that it is a combustible, valuable combustible. It was used since 60. And then this, when you consider Faecal sludge as a resource, you can see the impact is environment is cleaner, we enhance farm production, and in the 19th century, in Italy, the use of Faecal sludge allowed 4 dairy cows per hectare. And this was the starting point to develop the famous cheese, Italian cheese Parmesan. That's great. Now, just a picture on what is happening in Senegal. Senegal is a country that is a coastal country. We have nice seasides where any problem of sanitation is found. We used to show these pictures to our tourists. But we are also very problematic areas where sanitation is a big issue. We have, meanwhile, many, around 3 or 4 wastewater treatment plants. We have around 3 also Faecal sludge treatment plants. We have here, it's important to raise that we have suitable lands for cultivation, around 3 million acres, and only 2.5 million are cultivated due to lack of water. Lack of water, we are in an arid climate, and we have just only 3 months later. By that time, we are throwing at about 4 million cubic meters of sludge and Faecal sludge and wastewater. Our objective is the context in Dakar, about 70% rely on site sanitation. From that, half of them are using manual emptying due to high cost of mechanical emptying. Our research aim to add value to Faecal sludge so that we can impact financially the whole chain and reduce the cost of mechanical emptying, so that all the produced Faecal sludge can be traveled to the treatment plants. We saw that we can do it through 2 entry points. First entry point is trying to reduce operational cost of Faecal sludge plant through separation, improving separation solid liquid, through alternative filter measure, because we are having in those Faecal sludge treatment plants drying beds using sand as filter, and the sand is also used for building companies. This is a competition between the Faecal structural plant and the building companies. We also think if we improve drying process, we can reduce also operational cost of the Faecal structural plant. Through also valorization of end products, we can, by using dry faecal as fuel or by producing forage plant, we can also make money from the end products and also try to improve the whole chain of sanitation. Okay, we use some coagulants to improve separation of solid liquid in the sediment gas. If you want to have more information on this, we have this afternoon presentation on this issue by months ago. We, as you see, is a real improvement of the separation from the raw faecal when you add coagulants. And we also see that on calculation issues, we have performed more. We tried shell as a filter area. We tried also flint and we tried glass. Glass from companies that dealing with glass. We have the waste broken glass, and we also have many mining companies that are waste that have as waste stream. And as we are in a coastal area, we have a lot of shells. So we are comparing this filter to sand to see how it performs. The results show that this filter measure performs like the same than the sand. I picked this picture from the studies of one of our PhD students. Is also here. Is doing his PhD next few months. The conclusion is flint, shell, and glass can be used as filter measure pure pepper salt. We also try to optimize the drying process. We try to use greenhouses. We use also mixing. The results show that greenhouses work almost as rain cover, no significant difference, but daily turning reduce 20% footprint of drying process. So that's calorific value of dry fecal sludge comparable to the other solid combustible. This we do some calorific value analysis on dry fecal sludge, and we can see that really clearly comparable. Forest plant also, we tried 3 different forest plants, and we applied them plants. We applied them loads of 100 kilograms diameter, 400 feet, and we found that some of them do not like high concentrations, but some was happy with that. If we choose Baspolidium, we found that for the load of 100 kilogram metal, we feed 16 daily cows of 700 kilograms per month. This is also picked from our student, PhD student, which here who work on forest plant. We looked also on the quality of this forest plant, and we found that the quality was quite good. The conclusion here as the use of coagulum contribute to reduce fecal treatment plant footprint. Alternative major filter like shells, flint, or glass platforms are found, and greenhouses contribute to fecal drying half the rain cover, but more research is needed in this topic. They in turn contribute to reduce fecal treatment plant by about 20%. Use of fecal sludge can contribute artificially to fecal sludge. Thank you for attention. I want to understand funders one of both research and academic.
Question of law. Please.
Thank you very much, SuSanA from the International Water Management Institute in Ghana. I have a set of questions for you. The first one is, you showed how you use the set of coagulants to improve the drying process. So my question is, how much time were you able to save using those coagulants? And is it really beneficial to use them because there is a cost implication when you try to add a chemical or product to the treatment process? So how did you cost your process, and what was your finding on that? And then the second question is, you talked of greenhouse covering for your drying beds. I wonder how you did that. What kind of drying, how do you cover it? What kind of design did you use to do that? And then the third question is on your turning. How did you achieve the turning of the drying bed? I just wonder because the area may not be that high. So I wonder what kind of equipment you use for that. And then my last question is on your forage. The bacteriological quality of your forage. You didn't mention anything on that. Thank you.
Okay, thank you for your questions. Yes, for the coagulants, we use lime and muric acid, and also we use tryptophan. But this afternoon we will have more deeper information because there is one presentation which is going to focus only on how the coagulants can improve the drying process. But what I can say right now is we found that the separation of solid liquid in the settlement tank is so good that you have a cake that can be, you have less water in the cake. And when you put this cake on the dry bed, it percolates very nicely. And so you can reduce the footprint of the oil. That means you will dry your fecal sludge more quickly. Then you have, if the fecal sludge treatment plant is already designed, you can produce more dry fecal sludge. But if it's not already designed, you can, based on that finding, you can reduce the footprint. difficulty is present or its work is forced. You can quickly and just have more details.
Thank you very much. Perhaps we have not much time. Thank you very much. Thank you. Presentation on the composing of five and sludge from constructed land.
Good morning, everybody. My name is Jimmy Walker. I'm a PhD student coming from the University of York. My presentation this morning is titled Composting of Sludge and Macrophyte from a constructed wetland treating domestic wastewater. Nowadays, in the world, many countries, constructed wetland is known as viable solution compared to conventional system. In Africa, many countries adopt this system to manage their wastewater. In the case of Cameroon, since 2012, the government decided to build constructed wetland mainly in water in which the demand was higher. This is the case of Cité Verte neighborhood, in which a subsurface flow constructed wetland was built to manage wastewater coming from the government residential areas of Cité Verte. Despite the existence of this system and their performance, we have an important quantities of byproduct which is produced by the system. This is a big problem because sludge contains pathogen and heavy metal and cannot be directly used in agriculture or through discharge in environment. Co-composting sludge can be used to improve soil fertility because it contains of nutrients. Nowadays, co-composting is known as viable solution because of its low cost and its advantage to reduce environmental and sanitary risks linked to their discharge or to the reuse in agriculture. For this reason, it could be exploited in the wastewater treatment plant of Cité Verte if its operation process is mass spread. Our main objective was to provide a co-composting protocol that will help the exploiting staff to manage the byproduct collected at wastewater treatment plant of Cité Verte. To achieve this objective, three repetitions of two treatment, each 100 kilograms, was randomly set up in experimental design. Some chemical was analyzed in sludge, in macrophyte, and in co-composting, and in co-compost obtained. That element was heavy metal, exchangeable cation, minerals. Pathogens was also found using standard protocol. To assess the evolution of the maturation of compost during co-composting, some parameters were followed. We have color, odor, friability, pH, and temperature. These different parameters was monthly followed. Some annual test was used to compare results. After this methodology, the following result was obtained. Some heavy metal was found in sludge, but their concentration was low compared to French guideline. We have to say that we use French guideline here because in our country, in Cameroon, we not yet define guidelines. We also found MNX, but in very low concentration. This can be explained by the good hygiene conditions observed by the residents. About chemical in sludge and in plant, we found organic matter and some chemical, but those of sludge was much higher than those of plant. But regarding the CN ratio in plant, it was much higher than in plant compared to those of sludge. According to the evolution of temperature, we have obtained a classic evolution of temperature with three phases: a short mesophilic phase, a thermophilic phase, and a maturation phase. But the most higher temperature obtained was in the treatment tree, which contained 75 kilograms of plant and 25 kilograms of sludge. And in general, the different temperatures obtained here are sufficient to destroy pathogen. Many authors in literature show that between 45 to 55 degrees, the pathogen are destroyed in compost or in sludge. According to the maturation time, the treatment one, which contained 75 kilograms of sludge and 25 kilograms of hydroxide, which is the macrophyte, was the first to achieve the maturation. This can be due to the much higher quantities of sludge content. According to the physicochemical parameter of co-compost, different pipe or different compost were rich in nutrients and in organic matter. But those of some elements were significantly different in co-compost 1 and 2 compared to those of 3. Regarding the weight of different composts obtained, the weight of treatment 3, which contains 75 kilograms of sludge of plant and 25 kilograms of sludge, was much higher and significantly different compared to those of treatment 1 and 2. This can be due to the important quantity of macrophyte content, and that macrophyte contains lignin, which is not very biodegradable. The concentration of heavy metal in compost obtained was very low than those obtained compared to those of sludge at the beginning. But the concentration of chromium at the end was really higher compared to the French Gartman. At the end of this study, we can say that sludge of stable contains nutrient and organic matter, but cannot be directly used in agriculture because of the presence of heavy metals and pathogens. But the first treatment and the second treatment did not present a significant hygienic risk because heavy metals were present in trace level, and the level of element H was in accordance with French guidelines. At the end of the study, we can say that, in general, the treatment 1, which contains 75 kilograms of sludge and 25 kilograms of plant, was the best treatment because of its richness of essential elements and the short time of co-composting. Please permit me to thank this structure which supports us to achieve this work. We also thank Bill and Melinda Gates, which gave us the opportunity to be here today. Thank you for your kind attention.
For this co-composting consequence to the presentation. The burning question, just have only one questions that would be possible. Please.
What was the solids concentration of your sludge before composting?
The solid concentration was 70%. Yes.
Have you maybe considered keeping it for a longer time, like the initial treatment, constructive wetland, just increase the treatment times, and then end up with a drier cake? And now what would be the effect of that on the pathogens? And then if there would be a need for composting at all? Okay, so the question is, this is very nice research and it does make a lot of sense. And one of the reasons that we want to co-compost sludge and plants is because of the pathogen content. Okay, and the pathogen content is directly related to the dryness of sludge. So instead of 70%, let's say if you started with 85% or higher, the previous presentations had 90+% solid concentration in their sludge, and there wasn't significant pathogen. So the question is, if you start with a higher dryness, what would be the effect of that, impact of that on the pathogen content? If you consider that, and if you did not, it's okay.
Okay, we did not consider it first, because in this study, we use sludge coming from a wastewater treatment plant system. And wastewater here, and sludge in this study was collected from pre-treatment at septic tank.
Okay, only one question.
In your presentation, you indicated that one of the stress metals, I think, was chromium increase in concentration after cold digestion. What could they have caused that?
Please excuse me. For chromium concentration,
yes,
the concentration was not increased. No.
Yeah, you showed one of them that was that increased after cold digestion.
No, it decreased, but the concentration was much higher compared to French guideline. This is sludge, and this is the co-composting. It decreased.
It decreased, but it's not yet up to the standard yet. It's just that what you let us share. So maybe we can discuss about that later. So, the next of the discuss. Thank you very much. Another presenters to present about the applications of high organic loading rate. Maria Patrick from Brazil. So we moved out from West Africa, Brazil, and we're interesting to share experience from Latin America. Please.
So I'm going to try to be brief. I guess everybody's kind of hungry already. But so I'm presenting our study from Brazil. Well, but I believe that we are working kind of really like with the same objectives and in similar contexts. So I'm going to present about some trials that we did with application of higher organic loading rates in sludge treatment plants. So just for you to introduce you to our context, today in Brazil we are 109 million people, and from that amount we are 134 million people with no access to adequate sanitation. So everybody talks that, and that's right, that Brazil is like increasing and getting much and much better in economy and all that, but infrastructure actually it's not following this everything that it's happening in economy and all that. So we still have like really bad sanitation conditions concrete. And we do have a lot of on-site sanitation in rural and in urban areas. And I think that septic tanks they are our first the most used sanitation system in Brazil. And we do have guidelines, so we have some standards for the reuse of sludge, of excreta in agriculture. So we do have these guidelines, but we don't do that. So first we had the guidelines, and now we are trying to do something. But as you can see, we have like pretty much like high standards. So everyone that sees these standards in Brazil, the first thing that we think that those are like too high standards. So we're not even going to start to do nothing because we're not going to reach it. So, but this is what we have, and focusing on pathogens. So, as the previous presenters said, there is no like standard project criteria for sludge treatment wetlands. So this is one thing that we are looking for. And sludge treatment wetlands are not used in Brazil at all, but we do think that it's a really suitable sanitation solution for our reality. So this is just the type of sludge treatment wetland that we are studying, like a vertical treatment wetland with ventilation pipes. And this study specifically, we did a pilot system with 1.6 square meters, and we have this configuration. We have our support medium is made of 0.10 meters of sand, 0.15 meters of gravel, and 0.35 meters of large gravel. And we use a ventilation pipe, and we place like one ventilation pipe to each 2 square meters. So we see that this is working quite well for us. And the plant we are using is SuSanA bonariensis. For this loading height of 700 kilograms of total solids per square meter per year. This is a much higher loading height than what we have seen, but we do believe that we can push our systems to these higher heights if we have good conditions. Like the conditions that we studied, that we saw that this could make a big difference were like these ventilation pipes. The characteristics of our sludge, so it was pretty much like sludge from septic tanks, from domestic wastewater, and it was pretty much like with a good digestion condition. And we use this loading height we fed once a week. So we've evaluated the results I'm presenting here. They are for 5 months of operation. So we evaluated the sludge water. So I'm just presenting here the main results. And we've evaluated physical-chemical parameters and pathogens and microbial indicators. And then we did a small trial and we assessed the operation, and we evaluated the sludge accumulated in the drying bed, focusing on the reduction, of course, of total solids and also in the reduction of pathogens. And what we've seen is that the filter actually, it worked quite well with this high organic loading rate. And just pointing the main results here, we could have a decrease of COG like from 35,000 to 290. NTS also like a big reduction. Not as good as the results presented here using the loading gates of like from 100 to 200, but I think it can be worthy. Total ammonium nitrogen, also a reduction, and we have nitrate formation. So we've studied this a little bit more, and we see and we know that we can have both nitrification and denitrification in the future. We also have a good reduction of phosphorus in the orthophosphate cycle. So about the influence sludge and liquid percolated or sludge water, we had almost 3 log reduction of total coliforms, 2.5 reduction of E. coli, and 2.5 reduction of enterococcus. Still about this operation phase, the air temperature during the period that we evaluated, we had between 23 and 37 degrees Celsius. So we believe that we need to have at least this temperature so the process can really work with this high organic flowing rate. So we had like quite high water losses also during the sludge dewatering, like ranging from 20 to 60%, like depending on the batch. And this plant actually had a really good resistance to this high organic flowing rate. Of course, that in the beginning we had all this acclimatization of the plant. We started with smaller loading rates. And about the accumulated sludge, what we have found here is like the evolution of the sludge. This is why we were feeding just after we stopped feeding with sludge, and this is after 50 days of drying. So what we had, it's like a reduction of total solids content from 99% to 50 to 70% by the end of the process, like 50 days of maturation. And we did have a good reduction of, we evaluated human adenovirus, so we had 4 log reduction, this in 50 days. 3 log reduction of somatic coliphages. These 2 were like surrogates for human viruses. 2 log reduction of male-specific coliphages. And 3 log reduction of enterococci, and no salmonella detected in the sludge. We had salmonella in the influence sludge, but not in the accumulated sludge after 50 days. We did not find any acids in this sludge, but we are doing some trials in lab and pilots here. So these are the main conclusions. So we do believe that we can have good dewatering efficiencies with this high organic polymer since we have like good high temperatures and this plant specifically. But of course, what is the more studies are needed to confirm the sustainability of the system and to see if it's going in the long term. Thank you.
Thank you very much that we have learned from the Brazilian experience. That's one question.
Thank you, Mary, for the presentation. I am particularly interested in the plants you used for the wetlands. What was your choice? What was the factor that motivated your choice of plants? Because in Cameroon, we are into constructing wetlands, and we know there are the chlor, the steer, and other plants that we use. So, in as much as we are vying towards the advancement of the use of that technology, it would be interesting to know some other plants that would be very important, maybe have some qualities that we can test in the future. Thank you.
So we started shooting first about what plants we had there in the region, and that could be like suitable for the system. So we tried Zaniosys monagensis, that it was one of the best results, but we do have a lot of this plant there, so that's the main reason. And we've tried also Stifa dominiensis and Ciperus papyrus.
Thank you, very interesting results. If you're going to upscale it for small rural community, for example, how are your plans enhancing the dry process sludge or compost that we can call it, soil, and the plants? So I'm going to harvest those without damaging the underlying granulators.
Sorry, the last part?
If you want to harvest it, you probably need to walk on it with machines or even with human and wheelbarrows. How do you avoid destroying the granulators you rely on afterwards? So when you take off the plant and the vast or the sludge without damaging the underlying.
Well, I know that our system is quite new. The oldest that we have it for 3 years, but I know that there are some plants in operation that have like 10, 20 years. So actually, I think you have two choices. You can operate the systems for quite a long time. So if you have 20 years of operation, I don't think you have to be like much worried about, because when you remove it, I mean, you can start up again. I think that 20 years, it's a good time for a system to. But if you're thinking about reusing the sludge, I think it's a good idea to remove like once in a year or something. So, but for that, of course, you're going to take out some sand layer also, but I don't think that that's quite a big problem. I mean, you're gonna have to replace it, to put some more, at least the sand layer.
I think we have no time for further questions, but we have a panel. We have presented already, but there are some components. So they call Marie to present your FSM from technology to action, please.
Thank you. I will be presenting wastewater and fecal sludge management from technology to action. Case studies of Hanoi, Senegal, and Ivory Coast. Cameroon, like other developing countries, face different problems, such as high production of wastewater and fecal sludge, which are always discharged on the natural water body and open land, creating the open regional. These three pictures show the reality of Cameroon. However, various approaches exist, such as centralized approach, which are characterized by high cost to build, operate, and maintain. And developing countries always lack both the funding and technical expertise. The centralized approach, shown here by are characterized by the cost effectiveness. They are simple and flexible, efficient, promising and developing countries. Vertical consulted wetland are shown by this diagram, and those pictures are considered as an ecological approach for wastewater and fecal sludge treatment in tropical climates. The technology are promising and are considered to be a fascinating alternative for developing countries. However, the problem remains on how to operate without financial means order to remove nutrients and some byproducts such as land, compost, fertilizer, and water for financial needs. However, some limits are always seen on this approach because the only experimental or pilot plan are carried out, and we have few local experts available, and some weaknesses are also shown on the local research capacity and infrastructure. We have also lack of adequate educational and training programs, and infrastructure plan not always lead to business opportunities. The challenge also rely on the cultural barrier, such as political will, lack of the knowledge on the economic of management and reviews, the absence of regulation and legal framework, the absence of ethics, and also on how to capitalize on some sustainable aspects, such as you can see in Ghana, Dakar, Douala, and this study will be carried out, will be built on to answer on a specific question, so that what is the real need of added value of consulted wetland? How to fill in the gap between treatment option and institutional issues? What are the main favor points to build these innovative models? And how to increase their repeatability and impacts? How are the weaknesses of such models? What type of training do the agent needs? And what are the factors influencing the network formation? So our research aims to evaluate the effectiveness and sustainability of the option of wastewater Africa's sludge treatment in Cameroon, Senegal, Ghana, and Ivory Coast. Specifically, we will be evaluating the operational and technical aspects. Second, assessing the viability and sustainability of the system. Third, understanding and characterizing the relevant business models. And last, to raise awareness and knowledge. Regarding the methods, for the first specific objectives that consist of evaluating the operational and technical aspects, the study will carry out through scientific investigation. Regarding the assessment of the viability and sustainability, the study will be carried out through ecological, environmental, and socio-economic analysis and post-disciplinary study. For the understanding and characterization of the business model, will be analyzed and integrate quantitative and qualitative data. To raise awareness and knowledge, this part will be built on based on the building and training and strengthening of the capacity of the professional staff, maybe of municipality or local population, and at the end to evaluate the ecological socio-economic aspect. Studies will be carried out on in these aspects. At the end of our study, we are expecting to know the business model of such sanitation system, to know the impact of sanitation tools on the enhancement of food security and business opportunity. We will also know the ethical aspects of byproduct users, the economic, financial, institutional, and customer analysis. Also, we will build and we know the building and functioning lines with the limitation and opportunities. socio-economic, environmental, and health issues of the resource recovery of such treatment is also raised. The value chain of the production and packaging canal for byproducts will be also known, and the replicability scale of such enterprise will also known, and scientific publication writing and published in the peer-reviewed journal. Thank you.
Thank you, Dr. Kamari. Any questions for this planning case study to be done? Yes. Okay. No burning questions so far, just understanding. Perhaps because we are so hungry. Thank you very much, Dr. Kamari. So may I call for the presenters to come to the panel again, and then we will have a short discussion, panel discussion. Please come here. You have questions? Yes, please. Back side. Sorry, I cannot see. Yes, please.
Thank you very much to all the presenters. My name is Kofi and I work for the International Water Management Institute. I want to comment them because most of them are graduate students, PhD students, so it shows that many people are very much interested in water management. The one thing I found missing in all the presentations, in most of the presentations, is the aspect of the scalability of the innovation, of the technology that I've described. I wonder if any one of them can speak to that. And if you cannot speak to that, I think you should think about it critically. That we're looking for scalable solutions to FSM. So we need to be thinking about the feasibility of any innovation that we try to investigate. Is it feasible in that context where you're investigating it? How feasible? What are the challenges that will be encountered? I mean, you need to address something like that in your, whether in your dissertation or whatever. But if anyone can speak to that, I'll be interested in hearing it. Thank you.
Thank you. Very good question. I would like to answer on this at scale.
Fine. Well, thank you, Kofi. Just want to mention that we tested the scalability of planted dry lake at Dakar, and in 2009 with master thesis Francine she's in this room, but we have some questions that are not yet solved, so that we go to the experimental stage to solve this question before going again to the large scale, yes. But I agree with you that this point are remaining in the study.
Thank you. Okay, please, second, the last one. Especially this will start first, and then we move the...
Considering that farmers are potentially the end user of your compost or product, but farmers are also very good at dealing with organic matter. They are composting, vermicomposting, and doing all sorts of innovative technology, and they are very hands-on. They are focused on a high-quality product because they want to use it on the land. Are you considering to working with farmers as a processor, so advising them how to do it and supervising health issues and environmental issues, but let them do the job?
I have a long experience on working with farmers, and the point is use example composting is time-consuming activity. And I used to work with urban farmers, and they are doing intensive agriculture in a small scale, space, because due to lack of space in the city. And we train them a lot of time to do composting themselves, but we did not achieve this because it takes time. They don't have time to irrigate. Yeah. It's very difficult to bring them.
Okay, some questions there.
Yes, there are good presentations about wetlands and horizontal wetlands. I would like to know the efficiency of each unit. If I'm constrained by space, do you recommend me to use the two, or if I'm to use one, which one would I rather? The vertical wetlands and horizontal wetlands, which one do you rate as the most efficient?
I think the results from the two types of experimentations have shown that planted dry beds in terms of different quality are better than non-planted ones. So this is from different investigation that I'm carrying out.
Okay, please, the mic. Where's the mic? Okay, can you move the mic to...
Thank you very much. Well, I'm the chair of the IWA Sludge Management Group, and this was an excellent session, and I really enjoyed each presentation. And what was really neat to see is to see the performance differences from different regions and countries, and in particular in the final counts of pathogens and removal of pathogens, and that's really the most important factor in terms of the protection of public health. And maybe what I would like to highlight, and you probably noticed that from the data from Brazil versus other regions in Africa, in designing these systems, yes, loading rates are important. There are engineering parameters that we consider, but one of the most important determining parameters for the pathogen contact is the final dryness of sludge. And in some, there is a limit to that depending on the climate and region, and like in Brazil you reach 70%, 60%, and that's it. It doesn't matter if you wait longer, like the pathogen contact is not going to decrease more. But maybe what is more important to emphasize in terms of optimizing these systems is sometimes instead of following up with another process and making it a bit more complicated or complex, sometimes it also helps to just wait longer so that the final sludge is drier with the same engineering design, and then the pathogen contact will drastically go down. Thank you.
Thank you for the remark. Maybe the last one, then we can come up with a highlight point, please.
I'm William Sosra of the University of Kwazulu Natal in South Africa. I just wanted to know much about the effluent quality from the wetlands in Brazil. How much nitrogen is contained within the effluent, and does it meet the international standards for disposal into water bodies?
The effluent, we had about 10 milligrams per liter of nitrogen, like total ammonium nitrogen, and 10 to 11 nitrate. This is what we got in the sludge water. And we have like pretty strict standards for discharging water bodies in Brazil, but for nitrogen, it's above the standard. Like we have 20 milligrams per liter of nitrogen. That's what we can discharge in water bodies, and it's 10 milligrams per liter of nitrate.
Thank you very much. I think that we have enough of presentation and question and answer. I am understood that we discussed nicely that one of the suggestions is that at scale application, what should we do with that? And the second one is that about the pathogenic contamination in the sludge, in the effluent, what we should do next. I think I can conclude by 2 highlights. But the other lesson learned from this session, I would like to request any of you would like to address to the session here that what are the key lessons learned or the way forward that we should do in relation to the planted driveways or the constructed wetlands that we should do. Another one. Yes, please.
I want to share on the presentation of Guy Patel. It was a nice presentation. All presentations are good, but my lesson learned is that it makes good sense and it's a good research regarding the co-composting. We know that factory research give the here understood that and for the business because less amount of composting we have. But from the co-composting we can create a bulk organic. So there's a good indication which business has. But there is some confusion to me regarding the co-composting depends on type of organism. So there needs to further research.
Okay, thank you very much. I think another contribution to the lesson learned here, that would be very nice. I just like to share with you my experience that actually AAT is the one that we were the very first to do this kind of research. I'm also very happy that many of the schematic diagram that show in the presentation I used 10 years ago and then they still use that, and that would be nice. But not so lucky for me that I haven't heard the field scale application as my sister Funke has been mentioned that there should be at scale right now. So maybe the very last contribution from that gentleman. And the microphone there.
So what I can just talk really loud, that's all right.
Perhaps you can forward the mic.
My name is Justin with Columbia University in New York, and I think one of the take-home messages is that there is a lot of potential for sand or gravel-based treatment in terms of drying beds or wetlands. But I think one of the bigger concerns is when it goes to scale, what the longer-term maintenance needs are going to be, because it's clogging of all of the media and what's going to happen with drainage rates and all of that. So I think it's this looming question of if somebody's going to do this and it's a very large area, how do you end up maintaining it?
Yes, thank you very much. That would be one of the very good take-home lesson that we would need to have, and also like to share with you as well that either the planted driveways or the constructed wetlands, it seems to us that it is a natural system. We don't need to do anything else, but it's not. Really, we need an operation and maintenance. Even if it's not that having any machine or mechanical system to involve with that, no electricity, no moving parts of that aerator, for example, but still we need at least, for example, harvesting the plants or remove out the sludge from time to time. But for sure, the cost is much less than the mechanical techniques that I would like to share with you. But of course, the footprints that I'm very happy to hear that the very high hydraulic loading rate is still possible in Brazil. Then it could be a potential that we can look forward to either in South Asia, Southeast Asia, and many other countries, that if we can define very good plants that can tolerate such a very high loading rate, then we can reduce the footprints, the area requirement for the wetlands. That I just like to conclude this session before we have a good lunch. So thank you very much again for nice presenters at 6-1 and then